SDS-PAGE is a gel electrophoresis technique used for protein separation. After treatment with SDS, the proteins of a sample can be separated due to differences in their molecular weight. A sample containing a variety of different proteins can be analyzed. SDS-PAGE is short for Sodium Dodecyl Sulfate PolyAcrylamide Gel Electrophoresis. The proteins in the sample have distinct charges based on the composition of amino acid side chains. Proteins are folded in various shapes due to the polarity of the side chains and the non-covalent or covalent interactions. Upon treatment with SDS, which is an anionic detergent, the proteins are denatured. The disruption of non-covalent bonds leads to the unfolding of the proteins. SDS molecules will bind to the amino acid residues covering the proteins. Since SDS is negatively charged, all proteins possess a similar mass-to-charge ratio now as well, and this is the intention of SDS. Make the proteins similar in charge to separate them solely on their molecular weight. But before that, proteins might be also treated additionally with beta-mercaptoethanol. This substance is intended to resolve the disulfide bonds, which cannot be denatured by SDS. Beta-mercaptoethanol reduces the disulfide bonds. The protein sample was treated with those molecules, resulting in unfolded proteins, all having nearly the equal mass-to-charge ratio. To separate the proteins inside the sample, a gel is needed. This polyacrylamide gel can be divided into two layers. On top is the stacking gel, with a low pH to concentrate all proteins in one band. Below is the resolving or separating gel, which allows for protein separation according to their molecular weight. The gel is inserted into a chamber and everything will be filled up with buffer solution. The protein samples are then pipetted into the wells and the electrodes are connected to the power supply. When the electric voltage is applied, the negatively charged proteins will run through the pores of the gel from the cathode to the anode. In a heterogeneous protein sample, the proteins will travel through the gel with different velocity. Large proteins run more slowly, whereas small proteins will run faster in the separating gel. This separation works because of the gel structure. The gel is built up like a net or a sieve. Small particles can easily pass, larger ones take more time. In fact, we cannot see this illustrated separation directly. After running the gel, it has to be stained first. Therefore, one can use Comassi blue, a dye, to visualize proteins. After Comassi staining, the different protein bands are revealed. Traditionally, the first well might be used for marker proteins. This mixture contains proteins where the size is already known. The marker can be used as a reference then to determine the molecular weight of the proteins in the sample. When we want to identify or confirm the presence of a specific protein, the gel is used for Western Blot analysis, a technique based on antibody detection.